Hey guys, Dr. Darbro. This video deals with sampling distributions, more specifically the central limit theorem for proportions. So, and I'll just go ahead and warn you, this is some of the tougher material I think that we encounter the entire class. So, hang on for the ride. I'll do the best I can to make this as simple as possible. So, let's go for it. I think it's best if we look at what we've done previously and kind of embed this in previously learned material. And what we've done so far with the central limit theorem is we've looked at the distribution of sample means x bar. And we've seen that if we have a normal distribution, or if our n is large, typically we call large being 30 or larger, then our distribution of sample means will be normally distributed. We'll have a mu sub x bar equal to mu, which is the population mean. And the standard error will be sigma sub x bar equals sigma divided by the square root of n. Now we've worked on these problems for the last couple of weeks. So we're going to move forward and think about what happens when we have categorical data. Well, the first thing you have to keep in mind is we have new notation. First of all, the population proportion, which represents a percentage, is p. So you kind of think of p being our new mu. It describes our population just like mu did. The sample proportion is p hat equal x over n. P hat is just a count. So if you think about, if we take a sample of 15 people, and let's say we're looking at gender in a class, and 10 out of the 15 are female, then our sample proportion will be 10 divided by 15. So why are percentages categorical? This is something that gives my students fits every single semester at the college level. They look at 32%, they think, well, that's a number. So really, why is that categorical? Well, let's say we look at the following example. Studies show that 32% of Facebook users update their status at least one time per day. A random sample of 1,000 Facebook users is collected. 325 say that they update their status at least one time per day. Okay, guys, why is this categorical? Well, it's categorical because a Facebook user either does or does not update their status every day. What's the value of P? That's 0.32 or 32%, because that describes all Facebook users. And the value of P hat is the information that we get from our sample, which would be 325 divided by 1,000. We can express P hats as fractions, which is 325 out of 1,000. We can equivalently, that's a big word, equivalently express it as a decimal, 0.325, or we could also express it as a percentage of 32.5%. So gang, the central limit theorem tells us this: the distribution of sample proportions P hat, no longer x bar. So the central limit theorem tells us that if np and n times 1 minus p are larger than 10, then our distribution of sample proportions will be normally distributed. We'll have a mean mu sub p hat equal p, and a standard error of the nasty mess that you see on the screen. The guys down at the bottom, I made a note. Some textbooks, and I'm not really sure yet what textbook we're going to use for your class as I put this video up. It'll be clear, obviously, when you by now when you're taking the course. But notice that the 1 minus p under the square root could be expressed as q. That's common notation that you see in textbooks. Okay. So let's work a problem. Previous results indicate that 32% of Facebook users update their status at least one time per day. A random sample of 1,000 Facebook users is selected. What's the probability that 325 or more update their status at least one time per day? Conditions, are they met? Well, n times p is 1,000 times 0.32, which is 320. N times 1 minus p is 1,000 times 0.68, which is 680. And clearly both of these are larger than 10, so we're able to work the problem using the central limit theorem. Central limit theorem tells us more specifically the shape will be normal. The mean will be equal to p, which is 0.32. And the standard error is equal to the square root of 0.32 times 0.68 over 1,000, which is 0.0148. Guys, let's grab our calculator. If we go second function distribution, normal CDF, we're going to put in the lower bound. Since we want above 325, we have to put 325 divided by 1,000. The upper is going to be E99. Our mu is going to be 0.32. And our standard error is the square root of 0.32 times 0.68 divided by 1,000. Paste that into our home screen, and we get an answer of 0.3673. Guys, that's all I got for you. Next video I'll put up will be proportions and z-scores, and so see you then.